Let's get started. Should be available by now. I apologize for not doing it earlier, but both homework 1 and homework 2 solutions should be available to you. I did a content folder. I was hoping that the grading would have been done so you could have seen the stuff there, but I've been speaking to the grader, and so hopefully she's able to get stuff done in the near term. But you should also have all the solutions with any questions you would have. I go into a little bit of detail showing you the equations, but if there's something that's confusing, feel free to ask, okay? There's always the option if you want to do it by hand. I don't like to post the solutions until obviously after they're due for a number of reasons, but the biggest reason is if you look at the solution, you think you understand it. So my encouragement is don't just look at the solution and skim it and say, yeah, I got it, I understand it. Because remember, your brain has to wrestle with this information, and that's how you learn. And wrestling just takes time. So if you do it quickly, you might actually not know it as well as you think you do. Okay. All right. So this is in today's class content folder. So it is just an exam review, and it's wordy, and I apologize, but you can use it or not. It's just kind of like hitting the highlights of the relevant topics that we're going to go over that we've covered through this point in this semester, some in greater detail than other. But essentially what I'm trying to do is just give a narrative discussion of what the topic covers. I don't intend to get into a lot of detail here because you have, pages and pages of slides that you can take a look at. But the hope is that you can go through this and you can get all the information you need. Some of the basic stuff I haven't included because, you would have learned that someplace else, or it's so straightforward. Hopefully you don't have to spend a lot of time on it. So the difference between instantaneous, average power, and then developed power triangles. So we are in AC circuits. AC circuits is steady state. So we don't live in the time domain. We live in the frequency domain, right? Complex frequency. So we can get rid of all those sines and cosines that have omegas associated with it because we're looking over one complete sine wave. Now, the power that we have is only in the real world, there's only such a thing as instantaneous power. Just like AC circuit analysis, we have numbers that have complex parts. That's not in the real world, but it makes our analysis of AC systems so much easier. So we take that assumption about instantaneous power and only being in the time domain and actually average it out over one sine wave. And when we do that, we have the average power, P average. What we saw, though, is that if we have inductors and capacitors in our circuits, those have the ability to store energy for periods of the cycle. And so what ends up happening is we have to take into account the fact that there is energy that's being stored in those inductors and capacitors, and that is being sent back to the generators that are converting mechanical energy to electrical energy. So it's pretty important for us to see that we can't just throw those away. We have to include that. And what we did is we came up with the concept of reactive power. And reactive power is really important because it increases the line losses because it increases the magnitude of the current. So we have to keep in account reactive power and real power. And when we add those together, we add them algebraically, but keeping in mind, the Q part is the complex part. We get the total power, which we denoted as a new term called S, okay? And so we can build a power triangle. It's a right triangle because the J term rotates everything by 90 degrees. So P is our real part of our power triangle. Q is the imaginary part, or it's the one that's lined up with the y-axis. And then the vector sum of the P and the Q is the total apparent power S. And that is our power triangle. P is always going to be positive because the direction of current is actually determined by the direction of power, again, over one cycle. So maybe you taught in your previous circuit classes that you assume a direction of current. You're actually assuming a direction of power, and current is in the same direction. So a load, power is going in. A generator, power is going out. All right. So P is always positive. Q can be positive or negative. It really just depends on the type of load or how the generator is operating. And so what we have to do now is we have to introduce another term to really truly understand what our power going to a load or coming from a generator looks like. And that's whether the power factor is leading or lagging. Okay. And the power factor is the ratio of P over S. We don't even have to call it power factor. We could just say the current is leading or lagging, but we've just termed that to be power factor. So it really is about current, whether the current is leading or lagging. And then we say power factor just to know what the actual power factor is. And then you actually say it's the current is leading or lagging. So if you want to be 100% specific, it's a 0.9 power factor with the current lagging the voltage. Again, engineers are lazy, so we like to say 0.9 power factor lag with the assumption that you know that it's the current that lags the voltage. And how do we know? Question? Oh, do you want me to keep talking or wait for you to?
Voltage regulation. When you doing it with leading or lagging power factor, is it always inverse cosine?
For voltage regulation?
Yeah.
Well, voltage regulation, the calculation is just based on magnitudes, right? There's no angles. But when you do the current, if you're trying to calculate voltage drops through a system, including the current, then you have to do the inverse cosine of that to get the angle between the voltage and the current.
And it's inverse cosine, whether it's leading or lagging?
It's always inverse cosine. And the reason why it's inverse cosine has everything to do with the fact that it is a right triangle, right? This is theta. And we said that that angle theta is the cosine of that angle is the power factor. We defined it. Actually, we defined the power factor to be the ratio of P, whoops. Let's see if there's actually erases. Where's my eraser? I'll just do it this way. I'll just delete the whole thing. So here's P and S, and here's theta. And we defined our power factor to be equal to the cosine of theta, which is equal to P over S. The power factor is really defined as the ratio between real power and total power. And the trig identity, Oscar had a heap of apples, said it's the adjacent over the hypotenuse. So it's just a trig identity. That's the reason why we do the cosine. So it's always the cosine because the trig identity is what dictates what we use there.
Why is it inverse cosine?
Because I have a cosine of theta is equal to the ratio. If I want theta, I've got to take the inverse cosine of both sides to get theta.
You represent the power factor that's leading or lagging with just a negative for it?
No, I do not.
You just don't, you just ignore that part?
I don't ignore it. What I recognize is I say the power factor is leading or lagging, so I'll take the inverse cosine of the power factor to get an angle, and then I'll use my brain to say what is leading or lagging what. So I'll get, let's say it's 30 degrees, and if it's a lagging power factor, I will draw this, and that lagging, the inverse cosine tells me the 30, the I being below V or lagging the V is because of the lagging.
You just know lagging once you get that angle?
I get the angle, I note it, and then I draw it that way. If you get more comfortable, you can start to say, oh, I know it's plus or minus with I or S, but you can get easily confused if you just try to put negatives in there because you could put a negative when it really should be positive. Because this angle, I has an angle of minus 30, but if you did this, it's going to be some magnitude at an angle of positive 30. So that's where you got to be careful about just putting a negative in there, because if I said a lagging power factor, you put a minus 30 in S, that's the exact opposite of what it needs to be. It needs to be a positive 30 because of the conjugate term. Okay. Okay, so trying to remember what track I was on. Anybody remember what the last thing I said before the question? Which is fine. Asking questions is encouraged, so don't feel like you threw me off. I just started babbling and I forgot what I was talking about. So, well, maybe it'll come back to me. Well, I think I was going to get into Eli the ice. Was my next step. Yes. So we talked about lagging and the leading. And so the concept is you really rely on Eli the ice to tell you what the answer is. Okay. So even if I was to tell you on a test, hey, you have a resistive inductive load, what is the power triangle going to look like? You should know based on Eli the ice that in an inductive circuit, an L circuit, the current lags the voltage, right? That's what Eli indicates. In a capacitive circuit, the current leads the voltage. Okay? So pretty helpful to go ahead and do that. And then the other nice thing is that you can use your power triangles and you can actually look at how to improve the power factor. So if you have a poor power factor at a particular load, you can improve it. And a poor power factor is usually a lagging power factor, because what we learned a little bit with the transformer voltage regulation is once we started getting more lagging power factors, we saw that the voltage drop was more significant. So one of the things that we do to improve the voltage is we put capacitors at the end of the line where the load is, and then that counteracts the poor power factor, because in a lagging power factor, your Q is positive. With a capacitor, your Q is negative, and when you sum those together, it makes your overall Q seen from the source to look like a lower number. And since capacitors, you can just buy them and you can energize them, and that's all they take, is just a voltage source. They don't take any real power. It's a pretty cheap fix to improve power factor. Okay. I squared R losses are dramatically improved when you have lower magnitudes in current. So one student asked this question this morning about impedance. You've got to be very careful about when you use I squared R, V squared R, I squared over X, V squared over X, I squared times Z, V squared times Z, because all those equations are based on S equals VI conjugate. So it's okay to use the I squared R and the I squared X. It is not okay to say it's S equals V squared over Z or I squared times Z, because it's only going to give you the magnitude of the impedance. It doesn't give you the real part or the imaginary part. Okay. So be very careful and make sure you highlight this if you include this in your cheat sheets, that it's magnitude of I. It's magnitude of V. It is not I squared R. It's the magnitude of I squared. Okay. Everybody understand that? I'm trying to emphasize that because that's a common mistake. And if you give me a power on the test that has, let's see I'll ask you the question, what's the real power consumed by the load? And if you give me an answer, 524 watts plus J, 622 bars, I didn't ask for the bars, I asked for the watts. Okay. So you should only answer that question with watts. And I'm not asking for S, I'm asking for watts. So when you increase or question, you got to raise it high, because unless I'm looking at you, I can't tell. Go ahead. You will have a little bit of delta Y conversions, not transformers, but converting loads from delta to Y, which is just whether I multiply or divide by 3. And there is a problem on the test that it behooves you to do a delta Y conversion. Okay. So what I was saying is once you decrease the magnitude of S, because you've added a power factor correction capacitor, you decrease the magnitude of the current. So you get less line losses in your system. Your system is more efficient. That's why the utilities charge customers for poor power factor, because they're consuming more watts on the system because of the increased I squared R. And we did a bunch of examples, and I think there was one test problem, homework problem, where we actually sized a capacitor bank, and you can size them in ohms, but ultimately we size things in farads because that's what you buy or build. So you get the idea. Phasor diagrams. So a lot of what we do in electrical engineering is we try to make pictures out of things because it hopefully makes a lot more sense of what's happening. And drawing a phasor diagram tells you a tremendous amount of information about what system you're trying to analyze. And so knowing what a phasor diagram is will help you say, I can look at voltages, I can look at currents, I can look at the relative magnitude of the voltages and currents, and then I can make an assessment about how the system is operating. And if you become a power systems operator, so actually operating the power system, what you'll find is all they look at is magnitudes and angles of the system. So they're basically looking at phasor diagrams all the time. There's only such thing as a phasor diagram for phasors. That's why we call it a phasor diagram, right? We don't call it a diagram, we call it a phasor diagram. So the only thing that should show up on a phasor diagram is voltage and or current. You can't include impedance on a diagram. Why is that? It's not a phasor. Impedance doesn't rotate. There's no sign of omega t associated with the impedance. It's 3 plus J4 ohms. The sine wave doesn't change, 3 plus J4, where in a phasor diagram, you always have that rotation. So if you're trying to compare apples to apples, make sure you understand that a phasor diagram is for phasors only. Normally, we pick voltage as our reference, so we pick it as an angle of 0, just because it's easy to measure, and we can go ahead from there. But if you can do phasor diagrams, that will really help you looking at three-phase systems, because you can actually see with delta Y circuits, when I'm measuring VA to V, which is my line voltage, I can see that means VA minus VB. I don't know about an EC or even an EET, but when we use that convention here, it's VAB, which is plus minus. You put your red lead on the A and your black lead on the B, which is the same thing as saying VA minus VB, right? So when you are looking at phasors, you can actually just add or subtract vectors appropriately to check and see, do these things make sense? And you technically don't subtract vectors, you add the inverse of a vector or a vector that's been rotated by 180 degrees. So when you're looking at your phasor diagram, if you want to add vectors together or subtract them, just go ahead and swap, rotate your phase by 180 degrees. And it doesn't matter, it could be plus 180 or minus 180, it's the same thing. And you can get the results you need. When you add the vectors together, tip to tail, put the tail of one on the tip of the other, and then you can do your measurements that way. Since we're in AC circuits, we'll do everything with reactance. So we don't have LVIDT or CDVDT anymore. We only have JXL or minus JX sub C. We throw in the trash any mention of time. No derivatives there. Okay, that's one of the biggest advantages of AC circuit methods. The J term is just included there because we introduced a phase shift. You remember back at the beginning of the semester, we did the CDVDT, and when we did the calculation, if we ran a voltage with a sine wave to it, when we did the derivative, we'd end up with a cosine. And you can't compare sines and cosines. You have to compare sines and sines. And so when you did that, you ended up adding a 90-degree phase shift because a cosine wave is just a sine wave that's been rotated by 90 degrees. So that's where the J term comes from. It's literally because when you take the derivative or the integral, you end up with a 90-degree plus or minus phase shift that you have to account for. That's where that J term comes from. The 2 pi f is because you're taking the derivative of the sine of omega t. And when you take the derivative of the sine of omega t with respect to time, you have omega cosine of omega t. Omega is equal to 2 pi f. So where that 2 pi f comes from is just doing the physics derivative, going way back to your physics classes, 121 or 122 or 107, 108, when you actually had to look at circuit components. You just had to take the derivative, and that's where that drops out on. It's nothing magical. That's where all the application comes from. The really nice thing about AC circuit analysis is every single stinking circuit analysis technique that you've used works for AC circuit analysis. There's no adjustments that you need to make. KVL, KCL, loop equations, mesh equations, node equations, Thevenin's theorem, Norton's theorem, max power transfer, superposition. Running out of them, so if anybody's got one that I missed, let me know. All those are applicable, okay? So all the circuit analysis that you learned when you did DC circuits, it's the same stuff. You just have to do everything in complex numbers, all right? No changes. Let's see. So I think we talked about everything here. We already kind of talked about S equals VI conjugate. Go ahead, Drew.
I guess if you were to calculate Q using one of those equations, do you keep the J in there?
Excellent question. Do you keep the J with Q when you do the calculations here? No.
You have to keep the sign of it though?
Nope.
No.
Why don't you not have to keep the sign? Q is a real number, isn't it? You have
You just 9 degrees up or down.
it's up or down. Your power triangle tells you the direction, right? So when you do your phasor diagram, if current is lagging or leading, you can draw your power triangle, and then you just stuff in your value of Q, and then you know if it's up or down based on the power triangle you drew. So you don't keep the negative or the positive. that has to be drawn based on the power time. Same thing with P, right? Do we keep positive or negative with P? We just always assume it's positive, right? But if you had the direction wrong, you say maybe it's going in the other direction. So it's the same concept. Your power triangle will help alleviate any confusion with that. Don't forget to put that on your sheet. S equals V times I. Put brackets around I, put parentheses, conjugate. It's just the conjugate of I, not the conjugate of V. A lot of people make that mistake, and a lot of people will forget that it's S equals VI conjugate. Magnetics. We did a little bit of stuff on magnetics. Again, we don't need to be experts in magnetic theory. We just have to have enough to be confident in being able to understand how we convert electrical energy to mechanical energy, or electrical energy to electrical energy in the case of transformers, or mechanical energy to electrical energy. So we've already done a little bit of that with transformers, where we'd actually see magnetic fields and things circulating inside of a transformer. But in actuality, most of the stuff we're going to be interested in for this semester is doing things from an electric circuits to make mechanical or magnetic, electrical to mechanical, or mechanical to electrical. So understanding how we have reluctance and air gap, because in transformers, there's no air gap. All the windings are on top of each other, and then they're on the core that's solid. But in motors and generators, we have to deal with air gaps. Anybody want to guess what why? If there's no air gap, wouldn't the rotating part and the stationary part be touching each other? I mean, that's the definition of an air gap, right? There's no air between the two, which means they're touching each other. That's called rubbing, and you know, it wouldn't last very long if it's there. So you have to have an air gap to be able to allow rotation of the rotating part relative to the stationary part. So we have to understand the concept of permeability of materials. Important to understand how we can get MMF, magnetomotive force, which drives our flux through our core. We also have some leakages, and we saw that when we did transformer modeling. We had some leakage there, and we had some magnetize, and we have to magnetize our magnetic material and get all the norths and the souths lined up, et cetera, et cetera. Magnetic material, we talked about it being really poor as a magnetic conductor, or I shouldn't say a poor magnetic conductor. It's not that much better than air. When we think of electrical circuits, electricity does not flow in air all that well, right? We see it every once in a while in the form of lightning, but generally speaking, not every day you're going to walk by and see electricity just kind of flowing through the air. That doesn't happen that way. Magnetics, it's in this room. We have it everywhere. And that's primarily because magnetics can travel through the air without a lot of problems. So how good a conductor the air is to magnetic energy, it's not great. It's not like iron, but it's good enough that we can make it work. And the other advantage is magnetic energy. If you're traveling through the air, you don't lose any power, right? Because it's magnetics. There's no I squared R equivalent with flux. So you don't have the same losses. And that's why you can get, you know, at your house, you can get a 5-watt wireless router in your house, and you don't need, you know, mega power to go ahead and power that up. I think that's it. Oh, last thing, magnetic circuits, they tend to saturate because they are not great conductors. And so we run them at higher levels of saturation, which means they're no longer in their linear operating point. And so anytime you do things that are non-linear, you should, if you want to be 100% accurate, is you got to look at curves. And we in electrical engineering cheat that a little bit, because how many here has taken a circuits class with electronics? Everybody probably, right? Or just about everybody. And what do you assume in electronics classes to do your analysis? It's called small signal stability, right? When you run things at really low tight tolerances, you pick an operating point or a Q point on your electronics, and then you assume very small changes in there so you can assume linear operation. So that's why you set up a Q point, and then you only run a few milliamps away from your Q point, and then you can assume linear operation. If you assume operation of the entire device, it's nonlinear and the work becomes a lot harder. Then you got to go look at plots. In transformers, we tend to operate high on the saturation curve anyway, because the iron is heavy and it's expensive. And since we don't have any power losses, let's push the transformers harder and not worry about the fact that we've got some, some highly saturated material. It's not a huge deal. We can manage that. So use graphs for magnetic material. Three-phase, maybe or maybe not a new topic, depending on who you had for instructor. I know in the EET classes, they said they didn't really get into three-phase. Maybe they did, but they didn't. ECE, they barely covered AC circuits in 2 classes. So I would hazard a guess that you did not get exposed to three-phase power. But three-phase power is just take 3 single-phase power sources and reference them together in either a delta or a Y, so that you have all the power you need. Each one of those phases can provide a path back, a reference back to get to that power supply. We only talked about wire deltas. There are other configurations, but they're more advanced and they have to do with grounding or some special filtering. So we really won't get too focused on systems that are not delta or Y. We'll focus on the deltas and the Ys. So in a Y-connected circuit, the line voltage is not the same as the phase voltage. Remember, the phase voltage is across the individual power supply or individual load, whereas the line voltage is the voltage between 2 lines going to the load. All right? Those are very distinct. In a delta, the line voltage is the same as the phase voltage. In a Y, our line current is the same as the phase current. Again, the current that goes from the power source or from the individual element that is comprising, is one of the 3 elements that comprises your 3-phase load, that is the same, that's the phase current. So line current and phase currents are the same in a Y. In the delta, they are not the same because the line current carries the equivalent of the 2 connected currents at that location where you're tying. So using this table, hopefully will help you do it. If you get stuck, draw your phasor diagram, or just draw the diagram and see if you can see where the terms add together. It's usually easier to draw the phasor diagram because one of the things that when you do a connection diagram just showing the power supplies, you don't always see that 120-degree phase shift. So it makes it harder to represent that. So I always recommend just replace your power supplies with a phasor diagram of the voltages or currents, and then you can add or subtract as necessary. If we're ABC sequence, so phase A, then B, then C, we can see we have 30-degree phase shifts as mentioned there in a Y or delta. And I only talked about the ones that are different. So you can see in a Y, my voltages are the only ones different. My currents are the same. So I'm not going to lag or lead by 30 degrees if they're the same. That wouldn't make any sense. So we just talk about what has the ability to be different. So that's why in a Y connected circuit, we talk about voltages. In a delta connected circuit, we talk about currents. Same thing in ACB, and there are some ACB cases, not many, but when you have phase A, then C comes along, and then B. Remember, phase ABC or phase ACB are just what the end customer has called them. They might say this is ABC or this is ACB. That's just the convention that they use, because the winding that comes from the generator manufacturer or the generator itself is just 3 wires. It says H1, H2, H3, or X1, X2, X3. It doesn't say ABC. You get to put whatever one you want on. So there's no stipulation. Yes, sir.
So saying VAB leads VA is saying that the line to line voltage leads the phase voltage by 30.
Yes. Yep. That's correct. If you see 2 letters, VAB, that always means it's a line voltage. It could be the same as the phase voltage, but VAB means it's a line voltage. Okay. All this semester, we're going to deal with balanced systems, perfectly balanced systems, and perfectly balanced systems make the work a lot easier. Our phasors are always going to be the same as each other, right? Delta, then the voltages are the same. Y, the currents are the same. But in a, so they're always going to, but if they're not the same, then we have to worry about that 30-degree phase shift. And more importantly, we have to worry about that square root of 3. So the only time square root of 3 comes into play is when we look at phasors. Okay. When you convert impedances or power from single phase to 3 phase or back, you're always going to be using 3. The only time we use power, where we use a square root of 3, is because we got sneaky and we substituted in a line voltage for a phase voltage or a line current for a phase voltage. So it's just the math that we have to do it. But the base equation is 3 times the individual phase quantities. So if you ever get stuck, just think about it. Is this a phasor I'm dealing with, or is this another element, an impedance or power? And then hopefully what you've been seeing, if you've been doing the bonus transformer problem for the test, you actually see where you have to keep in track of the power, because those are 3-phase powers. You have to do some conversions to get single phase equivalents. So calculation of power, we're just going to add real parts and imaginary parts as necessary. So if you have a panel, or if you have an industrial facility with 10,000 different loads, you can calculate what the power demand of that facility is just by adding up all the real power, add up all the imaginary power, keeping track of the signs, or the directions, I should say, and then you can calculate your total power. Most of the things in your utility or your facility are going to be in parallel, so you just add them all up. Very few things are in series with each other. So that's what I say, adding them vectorially. Don't just say P1 plus Q1 plus P2 plus Q2. It's P1 plus JQ1 plus P2 plus JQ2, and on and on and on. Last topic's on the test, which is going to be transformers. The whole purpose of a transformer is to step up or down voltage. All its purpose is to do, well, voltage and or current. So every transformer that you see, it was originally intended to step voltage up or down. It might be that you actually use it for impedance matching, but the reality of it is it just looks at voltages or currents. And that's why when we talk about turns ratio, the turns ratio is A or N, depending on who you ask, and it's the ratio of the primary turns to the secondary turns. But an even better way to say that is the primary voltage rating to the secondary voltage rating. And since power and transformers are generally considered constant power, we did the derivation here, but the inverse of the turns ratio is what you get for current. So IP over IS is equal to 1 over the turns ratio, which is the good thing, because we don't want our transformer to increase the voltage and also increase the current. That's called a power supply. That's not called a transformer. So a transformer, if you increase the voltage, you've got to decrease the current proportionally to maintain that, because you're not putting any real power in the transformer other than the primary windings. So all that power, except for some of the losses, has to go into the secondary winding. If you were going to increase the voltage and the current through the transformer, you'd actually have some sort of other energy source to be able to do that. You're not stealing energy from the, the nether regions. It just is there. You reflect, so this would cause a little bit of confusion this semester. When we look at primary and secondaries, if we want to look at Thevenin equivalence of what an impedance looks like on the other side, you just have to reflect that impedance. So if there was confusion, I apologize for that, but that impedance lives on the secondary side. That's where my load is. But from the perspective of the source, I don't care that there's a transformer. All I see is voltage and current, which looks like an effective or a Thevenin equivalent impedance for representing the transformer and whatever load you have. So you just reflect that impedance onto the primary or into the secondary, just depends on which way you want to go. And you've got your ability, and that's using the turns ratio split. Okay. Question?
No.
Oh, sorry about that. So in that case, we were assuming everything was ideal and perfect. No losses, no leakages, none of that stuff, no magnetizing. In the reality, we have losses. Not huge losses, but losses nonetheless that we need to consider. And in some ways, that's a good thing, because if you continue on in the power systems world, if you will, transformers actually help you quite a bit to knock down fault currents. So you actually use them, you take advantage of them so that your fault current, like if you were on a transmission system that had, let's say it's 50,000 amps of current at 345 kV. If you were to set the voltage down to, let's say 115,000 volts, the fault current would be 3 times that 50,000 amps, 150,000 amps of fault current on the low side of the transformer. That would be very difficult to manage. That's a lot of fault current. Because the one thing about fault current is it doesn't care what the voltage is. The current is what does the damage. The voltage will just arc, but the excessive current will do that. So transformers actually can knock down the impedance without having really a major impact on the losses of a system. So that impedance that we have in a transformer is a good thing. That's sometimes why, if you saw in the problems, we talked about the short circuit impedance, one of the examples we had in class. We talked about short circuit impedances, but the transformer data sheet, it doesn't really show in there. There is a %Z term that, you know, if you really dig around, it makes sense to you. But the concept is that's what the effective impedance is of the transformer, and it brings the current down. And it also is because no real world transformer is ideal. They all have losses. And most of the time, unless it's a small transformer, and what I mean by a small transformer, I don't know if you would consider this, generally anything under 5 MVA would be considered a small-ish transformer, and it's an off-the-shelf item. You go to the catalog and you say, I need a 5 3/4% Z transformer with 13.8 to 480 volt delta Y, and then that's how you buy it. It's built off the shelf. Once you start getting bigger than that, you have to customize them, and then you can specify what %Z you want. Most big transformers have a much higher impedance than 5 3/4. They might have 9. I've even seen some as high as 10. Baby small transformers, like the ones that you see on the pole, those might have a 2% impedance. Because their job is not to reduce the fault current. Their job is just to set the voltage down, and their voltage regulation is really limited as what they can do. So you want as little voltage drop across those transformers as possible. But you can go to Eaton and you can look at their consulting specifiers guide, and they actually have right off the shelf, you can just order a transformer. So because we have real losses, we have to do tests on the transformers. You can't walk up to a transformer and see on the nameplate or see inside the transformer, there's a resistor with a yellow, red, blue color code on it, right? It doesn't work that way. So these are designed to do transformation. They're not designed to do any particular resistance. So you actually have to measure or calculate what the resistances are and the impedances are, and you use tests. And I really like this table. If you look at it, you might think it's really clever, or you might think it's really stupid. But I kind of put everything you need to do sort of in order of how you'd actually do that. So I told you apply the rated parameter, VOC, IOSC. And when we looked at that data sheet, we saw apply VOC on the lower voltage winding, because you can find a lower voltage power supply generally easier than a higher voltage one. Whereas in the short circuit, we do that on the other winding, right? Because we want to put a short circuit. So why not put the short circuit or drive the short circuit on the high side, put the power supply on the high side, because I'm just getting a piece of wire that shorts the terminals. Where with my power supply, if I have to provide 10,000 amps because I'm on a low voltage winding, that's a lot more expensive endeavor to do that. Anything over like 300 amps, you're probably running multiple or parallel cables to make that work, meaning you have to run more than one conductor per phase. I've seen 4 or 5, even some of these wind turbines, they run 6 or 7 conductors in parallel to be able to get the current carrying capacity that they have. So then we measure our parameter. We know what the voltage is or the current. So then we have to measure I and P. And after that, we can calculate everything else. We can calculate theta using our power triangles. Keep in mind, Eli, right? Eli is going to help you. Then you're going to calculate the impedance or the admittance. In the open circuit test, we calculated Y, and I just showed you, kind of all the stuff you need. In a short circuit, because everything's in series, you can just go ahead and calculate Z, and now you equate parameters. Your R sub C is 1 over the real part of Y, and your X sub M is 1 over the imaginary part. In the short circuit, you just have R equivalent and X equivalent. So because it's Z, it's just equal to the real or the imaginary part of Z. So this kind of just puts the whole spiel, hopefully in one sentence, so it doesn't cause too much argument, or one table, I should say. So one key thing is make sure you're on the right side of the transformer. Okay, make sure your voltages and your currents are reflected on the same side when you do your calculations. Otherwise, you're going to get wonky results. And that also applies for when you do the open circuit test. The open circuit test is on the low voltage winding. The short circuit test is on the high voltage winding. So if you want to build your equivalent circuit model, you either need to move the open circuit test to the high side, or you need to move the short circuit test to the low side, because the impedances aren't on the same side of the transformer. And so you have to kind of do that spiel. And then here's like specific test questions, what you really should focus on. And it's in generalities. So 3-phase, right? Calculate some phase quantities or line quantities. Power triangles and power factor correction. If I give you a simple series circuit, you should be able to do AC circuit analysis. Okay. And this is AC circuit analysis class. So don't try to do Laplace or try to do anything with differential equations. We're forgetting about that in this class. We're trying to make it easier. And I'm not saying you'd be wrong to do that, but if I'd go back to you and say, okay, what's the real and reactive power if you did your differential equation, good luck finding the answer, right? So let's do things the way we would do them in utility. Build a power triangle for a load and calculate any line losses. Another way to say line loss is I squared R. I'll give you an open or short circuit test or both. Calculate equivalent circuit data. And lastly, calculate some transformer voltage drop, maybe for percent voltage regulation. And that's it. So I've been yapping for almost 45 minutes. I'm sure everybody's completely tuned out. Now's your chance to ask whatever questions you have. Yes, sir.
Do you have examples for like?
Well, do you see one on one of the specific test questions? We certainly can do magnets or magnetic field, and you do have a practice problem or homework problem, but I don't know if spending a lot of time looking at magnetics is going to help you on this test. I'm not trying to, poo-poo your question. I'm just saying you have a limited time and resources, so spending a lot of time in that is probably not worth the investment. Unless, again, you got to take ECE321, which some of our friends in ECE either have or will be taken. And they're still feeling the pain if they've already taken it. Yep. Yep. Both sides. And I got to post this, but I will do this here. Let's see. Not there. So I requested a classroom because I don't think anybody would like to, you're welcome to, we could do a test. Hold on, we could do a test in the lab if you really wanted to, but I wouldn't think you'd want to do a test in the lab. So I have reserved WH140. Anybody know what WH is? No. Let's see. Probably going to be Williams Hall. So I will be there. It still shows little. So Williams Hall is the old Little Hall. As you can see, Google Maps doesn't have it yet. So we'll be in Williams Hall, room 140. And I'll be there from 8 to 10:50. On Monday? On Monday. Why did you do that? You want to be in that lab taking a test? With this many people? Why don't you get out of the way?
Williams 140's got the flip up arm.
Well, if we're all jammed in this room, you're gonna be happy to have that, right? I mean, at least you can spread out a little bit, so. I know it's not ideal, but I mean, that's the thing that we can have, so. I mean, the only other option would be we could do maybe Barrows 28, but I think Jude's using it at 10. So unless, do anybody want to come in and take the test from 7 to 9:50? Who wants to do the test from 7 to 9:50?
Is it,
Who doesn't want to do 7 to 9:50?
is there an option to do that? Is there an option for some of us to do it? Because I have class. at 10.
You probably won't need the extra hour. You'll probably be all set.
I could, it's project management.
I'll be there early enough. So I'll probably be there 15, 20 minutes early.
So if we get there like 5 minutes.
Yeah.
Oh, like something like that.
Yeah. Question?
Yeah, so instead of doing that, is not under the specific test questions.
Well, I didn't say that. Did you see that under there?
It's not under it.
So I wouldn't focus on it.
Okay, even though it's in the test review.
That's just giving you the whole spiel. You spent a lot of time learning this stuff, so I included it as, something that you would have learned, hopefully. So I did a comprehensive one. I can add a test question if you want. Question, Adrian?
So MATLAB, where do you use that all the time?
Yeah, so good question. It's an either option. You can use MATLAB or your calculator, not and. So if you have a calculator out, you have no computer out. If you have your computer out, I don't want to see a calculator. I don't want to see a phone either, because I know some people have calculators on their phone. They can add an app and make it that way. So you can use either one. And I'm not doing that to be mean to people, but my perspective is if you spent the time to learn how to use MATLAB, you've got your computer open, you're doing it. If you haven't learned how to use MATLAB and you're trying to use your calculator for most of the stuff, you could be looking and trying to get other problems and stuff like that. So this is just a way to help limit that, because most people who've done the time to do the calculator, the MATLAB stuff, they probably learn the material reasonably well. So it may not seem fair, but again, MATLAB is just a calculator. So you can use either one, but not both.
My question was if you don't have a phone, and that's really no.
You want to use MATLAB on your phone?
I mean, I could, but
You want to? It's the question.
yeah, I'd rather use it on my phone. It's just less. Takes less space.
You'd rather use MATLAB on your phone than on your computer with that little keyboard?
Can't really have.
You can't? Well, if we split up the desk, that's a big classroom, right?
Yeah.
Hopefully you can have your computer on the desk next adjacent to you. So. Yeah, I didn't even know MATLAB, you must be using the web-based one
No, it's an app.
on your phone? Wow, I didn't realize. I thought it was just like a web, because you used to be able to do it on MATLAB, but it was really, you had to go to their website and run everything off their website.
Yeah, no,
And you can actually have script files, you can save them locally and run it. Okay, if you want to, I mean, that's, like I said, I think the advantage of MATLAB is you have a whole big screen. And I find it easier to follow, but.
I understand. I was curious how you, your exams are set up. Are they, all multiple choice, or are they all open-ended?
Almost all open-ended. Generally, that's how I do it. I try to give extra credit. So here's the thing. I try to give extra credit, but I don't have any training in reading hieroglyphics. So if it's not easy to follow and not neat, I'm not going to spend, because I've got 30+ students in this, I can't spend 6 hours grading one exam. So if I can see it fairly quickly, I'll try to follow your path, meaning it's got to be clear. If I can't follow your path, then I'm probably not going to give you a lot of credit. And you're certainly welcome to say, hey, I do this, but I'm less inclined to give credit after the fact than if it's neat and easy to follow. And the other advantage about doing things neat and easy to follow is you get plenty of time. I'll bring plenty of scratch paper. Sometimes you make mistakes. So if you're rushing through and you just get, hand chicken scratches on it, then you rewrite it, then it's a lot clearer. It's easier to follow for you. And then you might actually say, oh, I made a mistake and here's a correction I need to do. So neatness counts.
I have a question about, technical, three things on.
Nope, I'll bring all the paper. Just bring your formula sheet and whatever calculator tool you want to use. You can bring some water if you want. When I take long tests, I like to bring water. It's early in the morning, but I'd always bring like a power bar or something like that just to get a little energy hit.
I know you may have answered it earlier, is that one side or double sided?
You can do double-sided.
They, exam, I can usually reflect on work.
They're pretty close. It's the concepts are similar, but they may not necessarily be the same. So I guess I have a different philosophy, which is from some of my colleagues. And my thought is that a test is not just to see if you can regurgitate the homework. A test is an assessment tool to see if you understand the material. So if I just gave you the homework over again, then that's just a process of can you memorize what was on the homework? So I really want to see what you learn. So that's where the problems will have similar concepts and methodologies will pretty much be the same. It's just that you might have to look at it from a different perspective. So it's not reinventing the wheel. It's just, if you know it, it's just applying the same stuff, but with a different question or a different way to pose it essentially.
So there's also an option to take the exam online next Monday.
Yes, so if you want to do it online, the test will be available at 8 a.m. You have to have a camera on showing your workspace. And you just have to have the workspace. Now, the other thing that's bad about doing that is you've got to get the stuff up by 10:50. So you don't have as much time for the test because you're uploading your stuff and making sure it's uploaded. And for some reason, this continues to be an issue with some students. I've had grad students struggle. You know, I would tell them you only have 5 minutes left and then they don't get it in on time. The upload screen goes away. So that becomes a real problem. And it has to be about equity, right? Which is if you turn it in a minute late, that's one thing. But what if you turn it in an hour late? That gives you an extra hour. So that's why I'm pretty rigid on that 2 hours and 50 minutes about uploading it, because I don't want a lot of people to turn stuff in whenever they want to. It has to be turned in right at that time. So that's up to you. If you want to do that, just send me an email because I've got to add you to the assignment for that. So I got to make that happen. I can't do it otherwise. So send me an email today or tomorrow, letting me know you want to do it online. Just make sure you can meet those commitments and we're good to go.
If you're doing online, should you run MATLAB on computer?
Yeah, it's the same. You can use MATLAB or your calculator. Obviously, you have to have your computer up because that's where the problems come from. But if you're using a calculator, I basically want to see you download the test, print it, and then use the computer just to show your workspace. Everything should be on a calculator. And then when you upload it, obviously you have to do the same thing. What else? TMI, too much information, or was this helpful?
You said that document was posted.
Yep, so I try as much as I can. So if you go under the 321 folder, and yours probably looks a little different than mine. So I do everything with content. And hopefully this makes it easy to find. And again, I'm always open to suggestions, but today's class is 2.8, and you already see there's one subset in here. So if you click on 2.8, there's the exam 1 review. And if you click on the exam 1 review, it should have all the stuff. And again, I don't sneak. I'm not hiding it. I put it there before today's class. I put it there, I don't know, a week ago. I did make a few changes, but I put it there a week ago. And I don't do that to hide things. I do that just so I don't want you to worry about other stuff. So if you want to look ahead because you got the time, great. If you don't have the time, you can focus on your other things until you're ready to start studying. So that's why it's available, but not required. And this exam review is not even required. You're not required to use it. If you have different ways of studying, it's totally up to you. Anything else? Yes, sir.
Would it be possible if you could do one of the problems on the one?
Sure. Which one? For homework 2?
Yeah. Start with that.
This one, right, oh, I put homework number 3, I'm sorry. We're not there yet.
That's not a sign.
No, because it's relying on stuff that we would be covering on Thursday, so. All right, number 3. This one?
Yeah.
So. Everything you need is right here. Right? All the tests. So if we follow along, we have my open circuit test. I have, essentially, this is all I have. R sub C and JXM. My voltage is 7,200 at an angle of 0. My current is equal to 0.45 and my P is equal to 355 watts, right? So all I need to do now is I do a power triangle, Eli the ice person, that says current lags the voltage in an inductor, which means it leads it. And I find that by taking 355 watts for my P and 7,200 times 0.45 equals my S, and my cosine of theta is equal to P over S. 355 divided by 7,200 times 0.45. Once I have this, we'll call this open circuit. Now I can say that Y open circuit, because remember, these two elements are in parallel with each other. And if I just did Z, I would have a hard time teasing out which one's is R sub C and which one is X sub M. So I take my voltage, my current, 0.5 at an angle of minus theta open circuit. I divide that by 7,200 at an angle of 0, and that's going to give me a YC minus a JYM. 1 over that is R sub C, and 1 over that is XM. That's the open circuit. For the short circuit, all I need to do is draw my transformer. And what elements are in play? Over here, I just have R equivalent and JX equivalent. My current here is 13.9. My power is 1275, and my voltage, one wake up, is 250. So now I'm going to go ahead and do the power triangle again. 1275, 250 times 13.9. That gives me theta. So now my Z, excuse me, is 250 at an angle of 0 divided by 13.9 at an angle of minus theta short circuit. And that's equal to R equivalent plus J X equivalent. And once I have that, the only thing I need to do now is look and see, well, both of these tests are on the primary winding. So if I draw my equivalent circuit, I have my R equivalent, my X equivalent. So this is R equivalent, JX equivalent, R sub C, JXM, and then my transformer is shown here, and this is the 7,200 side, and this is the 240 volt side. That's the equivalent circuit. Sure.
Is there any piece of information to be given to divide it up into primary and secondary resistance of these instead of just having your equivalent?
Yeah, so the only thing is, if you recall, R equivalent is going to be equal to RP plus A squared times RS. And the normal assumption that we make is RS is going to, well, we basically say that these two are equal to each other when you reflect them through. So RS equals RP divided by A squared. So you can substitute there and then you can solve for each one individually. So you set the reflected ones equal to each other. And it's the same thing with X. That's just a That's the thing we do in education. I don't know if anybody in the industry does it, because normally they only care about the equivalent values. They don't care about what it is on each side. They just care about what it is from the box perspective, the in to the out. What else? How about TV land?
All good for me.
Okay,
All good.
thank you. Yes, sir.
Can I do some problem on calculating a voltage drop?
No, not at all. So if I've got a transformer that has, let's say it has an X equivalent, we'll just say X equivalent equal to 10 ohms. So we could do it a bunch of different ways, but let's just talk about it from voltage regulation. Let's say it's a 7200 to 240 and it's a 10 kVA transformer. I'm trying to drive my load at plus minus 240 volts, and I want to deliver 10 kVA to the load. So let's just say it's operating at a 0.9 lagging power factor. So now I calculate I of the load, which is going to be equal to 240 divided by 10 kVA. And the angle is the negative of the inverse cosine. Nope, I got that backwards. Sorry. Let me erase that. Other way around. It is 10 kVA. My angle in negative cosine inverse of 0.9, and I divide that by 240 at an angle of 0. Once I have that, now I can redraw my circuit. This is J10. This is a load that I don't care about. And this here is what my power supply, my current drop is, I load. So now I can calculate the source voltage on the secondary side of the transformer. Because I know this voltage is 240. I can get a voltage drop here, and then I can calculate VS. What it actually needs to be set at to deliver 240 volts magnitude voltage at whatever load demand is. Once I have that, and then I can do my percent VR. V no load minus V full load over V full load, multiply that by 100. And I can do my percent VR. But literally all I'm trying to do is get the equivalent voltage drop across the transformer. So if I just said, what is the voltage drop across the transformer? You're done right here. Once you have this step, you're done. Voltage regulation would just be the next step to include that. And remember, your percent voltage regulation is a percent and it's magnitudes only. Don't include any angles. If you give me a percent voltage regulation of 3.2 at an angle of 25%, probably not going to get full credit. Okay. What else? Everybody's very quiet. That's making me nervous now.
We also have to do, copper loss.
Sure. If I have an R equivalent here, the copper losses is just the magnitude of I squared times R equivalent. So once you know what the current is, just take the magnitude and then multiply that by, square that and multiply that by R. Copper losses is the winding losses essentially.
We're not gonna have problem for loss. Right?
No, because normally they'd be given to you. So don't look smiling. Usually when you did run the people like, yeah, I'm feeling good and I feel better. And I'm seeing long faces, so I'm nervous. Do you not like having a test on Monday? I know that's after the weekend.
Nah, usually people get ready 5 minutes before the test.
Gotcha. Then they're fine.
Yeah, that's why we be like, yeah.
There's only one problem. Would you rather have the test on Thursday? I'll give you an hour and 15 minutes though.
And if we done it an hour.
I write the tests so that you should be able to get it done in an hour and 15 minutes, but I don't always know what people's abilities are, so I don't want to say that definitively.
How fast can you do it?
I think it took me 10 minutes to do it. But that's not a fair comparison because I kind of know what I kind of know how to do the problems because I write the test. So it's not like I just, looked at it cold. It's just one of those things where I wrote the test. If you wrote a test, it would take me longer because I'd have to think, okay, which equations are we using here and that type of stuff. So it'd be,
Okay, so if you say give it to John, you'd be able to do it in less than 30 minutes.
maybe. Not because John's not a smart person, it's just that he doesn't cover the stuff, so he might struggle with power triangles or three-phase power because he doesn't cover that all that often.
So it might. An hour to 2 hours.
Well,
Yes.
no, the only reason why I say John, again, is he maybe hasn't done three-phase power in a couple years. So he might not remember all that stuff. He would say, oh yeah, three-phase power, but it's just not familiar to him. Like if you asked me to go take a test in electronics, I would do the same thing. I'd have to figure out like, okay, what's being tested and what's relevant. I'd have to study. I mean, if it's less it's something that I teach or do on a regular basis, I have to spend time because I can't memorize everything. So op-amp circuits I can do, but if you said, here's a BJT and go ahead and analyze it, it would take me, I'd have to look at it and process it. Yeah.
It's only been like 2 years. No, it's not even a year.
I get code.
We have 8 minutes. Anything left? Yes, sir.
So $50 and 60, right? Fine.
Yes. Unless we start getting into machines or sometimes you're looking at 50 hertz machines, it'll be 60 hertz.
If I'm gonna take the online thing one day, would I even like on a picture of it?
Yeah.
Yeah.
Yep. As long as you've got a decent phone, the quality on a phone is pretty good typically.
You want, yeah, right.
It would be better to have PDF because if you send me photos, they get out of sync and it's very hard to grade if page 1 is down at page 4. And then remember I said, like I have to grade 30 of these. It's hard to be able to go up and down and do it. So usually it's better just to import it into a Word file and then plot it as a PDF, and then you can do it that way. It only usually takes an extra minute to do that. So make sure I can see it too. That's the other thing too. It gives you a chance to proof it and see if it's legible. The advantage of coming to the live class is you just turn in your exam when you're done. You don't have to think about all those things. Yes, sir.
You want to just questions, are there any?
Sure. Yeah, I'll answer any questions. And even the online people, I will set up a waiting room and I'll just answer your question specifically. So I show up with a headset and then I do that way. If it's something that I think the whole class needs to know, I will make an announcement. Anything else? Going once, twice. All right. Have a great day, great weekend, and I will see most of you on Monday. Take care, everyone.
See you Monday.
Yeah.